let's start. So today we are going to look at some introduction to the RISC V IEC. And then I asked you to print something and bring to the class, like this two. I hope you guys will have them. Now everything, the whole entire, I mean from here on, the whole entire course is going to be based on only these two sheets. So if you understand what these sheets are, I don't think there will be any class anymore. Right? I mean, so if you're given sheets like this, you need to be able to understand what it is, and then you need to be able to understand what everything within this one is, and then what it does, right? So do you know what this is? I mean, do you know what this is? So if I give you something like this, just hand you something like this, what do you think it is? What? Yeah. Yeah, so what we have done now, what we have done so far is that we have looked at the individual components of the CPU, right? So now, from the scratch, you can actually implement all of these components. I mean, that's what we have done for the past 2 weeks, or is it 3 weeks, right? We learned how to design the register file. So if I give you some specification of any register file at all, you should be able to design it from the scratch, right? So we learned how to design memory. So I give you memory, I give you the memory with the dimensions and stuff like that. You guys can design it from the scratch, right? Then you guys can design the ALU from the scratch, right? So I mean, everything is there for you, right? I told you how to design all of this from the scratch, and then I even have video evidence of that, right? So now these are the hardware components of your CPU. You guys know that already, but we are missing something, right? You guys obviously know we are missing something. So for this one to work, for all of these components to work within the CPU, we are missing a very important component, right? What do you think we are missing? Yeah, so we are missing some instructions, right? So what should everything do? Like, what is the purpose of each of them? And I think you guys know that already, right? But you know that the CPU, all it does is that it reads instructions from memory, right? Then it decodes the instructions, and then it executes the instruction, and then either write back to memory and stuff like that. That's what it does. So it needs some code to read. So what code does it read? Right? So that's what you are missing. So that's what we are going to be studying today. And then we know that for the normal internal architecture, you have seen the control logic. I know that you guys know that there's some kind of control logic within the CPU, right? There's the ALU, there's the register file, and there's what is known as the PC. You guys know this already. You know what the PC is? What does it do? It stores what? It stores what? So, it stores what? It stores the what? Anybody else? What does the program counter do? It does what? Yeah. Right? So it stores the address of the next instruction. I mean, I know that probably you guys know this definition, but you don't even know how it works in real life. You know that it stores the address of the next instruction, but what does that actually mean? You don't know what it means. So when you look at the architecture, right, you see that there's memory here, right? We have the instruction memory. That's where the instructions are stored, right? So the instruction memory looks like this. I think I've always drawn a memory like this, and then I say that we have some addresses say 0, 1, 2, 3, 4, whatever, right? So these are addresses, right, to that memory, to this instruction memory, right? The instruction memory has a data weight, and then it has a depth, right? So what your CPU does is that it reads from your base. So when you start, you have to give it the base address. So the base address is where it starts from. So let's say your base address is 0, right? So it reads instructions from this portion of your memory. So the 0, it goes to the 0 address, then read the instructions, then it decodes the instruction, right? Then it executes the instruction. Now after that, it needs a way of knowing where the next instruction is. So that is where your PC comes in. So your PC is also, your program counter is also a register. And then you know that registers can store data. So this register will store the address of the next instruction. So if the instruction address was 0, after it has read from this instruction address, it will increment this instruction address to 1, right? Right? So after it has finished executing the instruction in 0, then it will read the register file and see that, oh, my next instruction is in address 1. Then it goes there, read the instruction and decodes and does whatever you want to do with it. Understood? Yeah, yeah. Okay, so as I said, the CPU, all it's doing is that it's reading from memory, it's decoding, it's executing, and then every time it executes, it has to update the PC, right? You just increment it and stuff like that. But so you know that if you write in your coding, if you write something, you guys have done any hardware coding before. Have you guys done any hardware coding before? No hardware coding at all. None, like not even one hardware coding. So what makes you different from the guys doing computer science? Eh? Or you guys are the same? The what? Mass. What makes you different from computer science? Eh? Or because you guys are in different faculties or different departments? It has a difference. No, but I think you have. So if you code something like if you code something like memory in bracket, square bracket PC, what does it mean?
You want what is at maybe the busy is
Yeah.
one. Which you are saying you want what is at
Yeah.
one of the memory.
Yeah, it's as simple as that. So the PC is just a number, it's just an address. So the PC will be 10 or something like that. So once you put 1 here, so it goes to the memory and then picks out that location and then it's that easy, right? So now what you're going to look at is that we have looked at the hardware. So the hardware is what is below your hardware is what we looked at. So it's what is below the IAC, right? The instruction set architecture. So your hardware is below it. We have looked at the instruction set architecture already. Now your software is above your IAC, right? So because you find it difficult to actually write hardware codes to interface or to actually communicate with your hardware itself, you actually use your software to communicate with your hardware, right? But that is the work of the computer science, right? They study the software version, the software side, right, of computing, and then they are able to write programs that will talk to the hardware. Now, you as computer engineers, you study the IAC, the instruction architecture level, down to the hardware. So that is the main difference between you and the computer scientists. You should know how to actually implement a CPU from the scratch, right, in hardware, and how the hardware behaves. They have to know how to program in software, and then actually upload the codes, and then it will work in the hardware. Right. So your job is to manufacture the hardware itself. So you don't deal with software at all, just the hardware. So it means that, and then the hardware starts from the IAC, the instruction set architecture. Understood? So because you two as computer engineers, you can communicate directly with the hardware using machine language, right? At first, some years ago, that's how they actually communicated. You know that your hardware is just about, as I said from the beginning of the lecture, it's just zeros and ones. Your hardware understands zeros and ones. The underlying architecture is that it uses what transistors, right? You guys know that. So the transistors understand only zeros and ones. So at first, that's how they actually program in zeros and ones. So you write 000, and then it means something, and the hardware will actually behave in a way, right? But because you are not able to also communicate that nowadays, and then it's too tedious with the kind of chips we are actually producing with so many millions of gates within a chip, you can communicate using machine language, zeros and ones. So you also make it easy for yourself a bit by actually knowing what the ISA is, right? The instruction set architecture. So the instruction set architecture is just a simplified version of the machine code, right? So once you understand the instruction set architecture, you can now design your own CPU and stuff like that. Understood? Right. So now, for you to actually design your own CPU, you need to code in hardware language. We have we have two main hardware languages. We have the VHDL, then we have the I think HDL. Oh, VHDL and Verilog, right? So as computer engineers, once we go anywhere, everybody will be asking you, what language do you use? Do you use VHDL or do you use Verilog? Nobody will ask you what do you know Java or do you know C++, right? They'll be asking you what language do you know, and then once they ask you what language you know, you should know that they're talking about VHDL or Verilog. And then based on where you studied, right? Based on the country you studied, you're either using Verilog or VHDL. If you study in Europe, they mostly use VHDL. If you study in the Asian countries like Korea, China, and stuff like that, they use Verilog. But essentially, they are probably the same. They are the same, but a little bit different in their syntax and stuff like that, right? But because we don't have time to go and learn a whole programming language from the scratch again, right? I think you guys have how many weeks more? 5 weeks more. What? 4, 5, 4 weeks more. 4. I thought it was like 2 weeks more. 2 weeks more, right? I'm even tired, Chuck. Okay, so now the most important thing is that you know that there are companies that produce these chips, right? The CPU itself. So once I say the companies that produce the chips, I'm not talking about a company that produce the entire PC. You know that there are companies that produce only the chips, and then other companies buy this chip from them, and then they also use it to produce the entire PC, right? You guys know this already. So you guys know that Intel produces some kind of chips, right? You know that ARM also produces, right? And then you know now the new one is the RISC V. That's what we're going to study. Now so why are we even going to study the RISC V instead of studying something like ARM or Intel, right? Who can tell me why we are looking at the RISC V instead of ARM or Intel? Yeah. Yes. He said he didn't hear you.
Said it's open source.
Yeah, so the RISC V is open source, right? So the most important thing is that, so what they do is that Intel, and then every company that produces their CPU, they have their instruction set architecture available. Yes, right? It's available. They show you how they are producing their CPUs. but you can only study it, but you can't use it. So if you want to use an ARM processor for your project or for whatever you are doing, right, you need to buy it from them. So they give you a license, right, and then that license expires every year. Wow. You guys don't have standby generators. Okay, so so the, the ARM and then the Intel give you the ISA, the instruction architecture, and then how they produce their CPU. But you cannot take it and also go and produce your own, right? Because they have licensed their instruction set architecture. They've licensed it in a way that you cannot use it commercially or even for academic projects. Understood? So before you use their processor, what you must do is that you must first contact them and then they give you a black box of of it. So when you are coding in hardware, and as I said, you have VHDL or Verilog, right? You have some kind of some codes. Some codes are actually like black box, right? You have they give you the code, all right, but within the code they have encrypted the code, right? So they give you access to only the inputs and then the outputs. So they tell you that if you give it this input, it gives you this output, and then that's all you need to know to use that kind of code, right? So you take the code, put it into your code, and then you give it input, and then give you the output, and then stuff like that, right? So they have encrypted their code itself. You don't have access to it at all, right? So now, if you take an Intel or ARM ISA, and then you produce your own CPU, right? And then they get to know that you're producing your own CPU. You know that their lawyers are coming for you, right? And then, I mean, if you are unsuccessful, like your product is not commercially successful, I mean, nobody cares. Of course, nobody cares. But as long as your product becomes successful, like people are actually buying into your or buying your product, you know that they will come for everything. Like you'll be left with nothing. Right? So that's why for you to learn the architecture of CPUs nowadays, you have to learn the RISC V, right? It's open source. It was developed probably in 2010 or so. Yeah, it was developed in 2010 in a university, right? So it was developed by people like by guys like you. They were doing what? On somewhere. So the point is that what they do is that I don't know about here, but some universities, every every lecturer has a lab. You know that, right? Yeah, I mean, if you go to K University now, I think they have that. I don't know about here. I don't. They don't have that here. So if you go to K University, every lecturer has a lab, and then what they do is that they seek funding, and then they pick students from. They pick some number of BSc students. So if you have a lab, you pick some BSc students, you pick master students, and you pick PhD students, and then you give them a project to do, right? And then they execute those projects, and then you use those projects for your funding and stuff like that. So you give them rules; they must come to the lab. It's just like a normal working environment. So once they are studying, they are also in the lab. So if they are not in class, they are in the lab. So they are employed like some full-time employees. They get stipends every month for that and stuff like that. So it means that by the end of like studying for their BSc, so they are so advanced in that level because they have actually implemented real stuff and then real world kind of designs, right? So once they enter into the workforce, they are completely different from somebody just coming to class and going home, right? And then in the same way, once you leave here, right? Once you finish like here, and then you go outside to go and study for your masters or some stuff like that. Like you go to place like South Korea and stuff like that. So that's the same thing. So, well, I mean, before you get there, so for their schools, for masters and PhD, you pass through a professor to get there. Each professor has a lab again. So once you apply, the professor picks you, and then you go there, and then you are in the professor's lab. So you get to realize that once you get there, the professor has BSc students, master students, and PhD students, and then you get to realize that even though you are studying your masters, you're going to be compared to their BSc student. You're going to be compared to a third year BSc student in that lab once you go there, right? You know that because from his first year of studies, he has been trained to use each hardware to, like, if they're studying computer engineering, right? They have used all the standard industry tools from first year. That's what they study, industry tools, industry tools, how to use them, how to code in hardware, right? How to develop hardware products and stuff like that. That's what they're studying. So by the time they get to year two, they've already studied all the tools. They are doing research, right? So now that you live here and then you go there, it means that the background is your background is more theory even, and even with the theory you don't even understand it. I mean you don't even understand because you are not doing practicals, right? You don't even know the worth of the theory until you get there. Then you don't see the tool itself, and then they're using the tool itself. But of course, after once you stay there for 1 year, 2 years, you actually catch up to the master students and then their PhD students. It's not anything because the point is that once you get there, you'll be in the lab from 10 a.m. to 10 p.m. So what will you be doing from 10 a.m. to 10 p.m. for like 2 years straight? So it means that you will be able to catch up. Understood? Right. So I mean, so here, oh, I can't project anything. So the most important thing is that for once you are given a CPU, right? They give you the base of the CPU. They just say, oh, this CPU is either 16-bit or 32-bit or 64-bit, right? So if I give you a CPU and I say that this CPU is 32-bit, what does it mean? The input stream. You are adding software and hardware input, then stream. Hurry up, hurry up. I mean, this is just a basic question. Oh, this Intel CPU is 32-bit. What does it mean? Effective what? Effective 32-bit. I mean, I mean, you have said something. Speak a little bit.
It can handle two-bit instructions in one process.
It means what?
It can handle
Pay attention.
it can handle 32-bit instruction in one clock cycle.
No. Yeah, he said almost the same thing. Uh-huh. I mean, it's all you're always saying the same things in different ways. This CPU is 32 bits. What does it mean? So, 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 common sense, right? So common sense, right? You have to go into it. You have to go into the architecture of the CPU. So you have to start thinking, okay, what is one of the most important components within the CPU? That's what you must think first. So if they say this CPU is 32-bit, so you have to cast your mind. Oh, what is the most important components there within the CPU, right? So what do you think is one of the most important components there? So okay, let's go here. So this is the architecture of the internal architecture of a CPU, right? What do you think is the most important component here? Now you must be aware that the memories normally reside outside the CPU. So forget about the memory, the two memories there, right? So now just forget about these two memories, and then look at this this architecture. I mean, they are just two components here. So what do you think? Which one do you think is more important? The early is more important. Why do you think it's more important? So if I say this CPU is 32-bit, so how will you relate that to the ALU? 32 times calculation. Okay, so now the most important component here is the register file, right? Each CPU has a register file. Each CPU in the world has a register file. And then the CPUs differ. Like one of the main differences between different CPUs is how they implement their register file. And then if I say how they implement the register file, I mean the data weight or that the register file is just memory again, just like memory, right? It's just memory. And then as all memory, we have what is known as the data weight, right? And then we have the what? The depth, right? So these register files are individual registers, right? So each CPU has a fixed number of those files, right? So there can be probably 100 of them, 200 of them, or 300 of them. But what we care about is the data weight of each of them, right? So if we say this CPU has 32 bits, is 32 bits. We are referring to the register file, the data weight, the register file within that CPU. Understood? Okay, so for the Intel, right? The Intel has 16-bit, 32-bit, and then 64-bit versions of their CPUs, right? The ARM has 32-bit and 64, and then the RISC V has 32, 64, and then 128-bit, right? So now the Intel designed their first CPU in 1978. ARM designed their first one in 1985, but RISC V designed their first one RISC V came in 2010. So RISC V is actually fairly new, right? Now the design, you know that the Intel design is CISC, the RISC V, and then the ARM is RISC. And I believe that in studying computer architecture, when you guys know the difference between a CISC computer and then a RISC computer, right? What does a CISC computer mean? Six computer, CISC. CISC and RISC. You guys have seen it in computer architecture, I'm sure. Hurry up. CISC and RISC. I think you guys have seen before. CISC RISC. Okay, what is the full meaning of CISC?
Complex instructions.
Architect, computer. And then what is RISC? Instruction set. So it means that you guys just know definitions, but you don't know what what. So each CPU will be either a 6 CPU or a RISC CPU, right? So one is complex instruction. So from the meaning, it means that yeah, instruction set is complex. And if I say complex, what do you mean by that? If we say this instruction set is complex and this instruction set is reduced, I mean from the word itself, you must know what it means. So for the complex instruction set, right, it means that there are so many instructions within the IAC. For the reduced, the, the, there are a few instructions within the IAC, right? And then if you have these two architectures, if I say, oh, this instruction set architecture has very complex, so it means that it has a lot of instruction sets, a lot of instructions within the instruction set. And then if I say this one has reduced instruction, very few instructions, what do you think is the advantage and disadvantage of both?
You can do more.
What do you think is the advantage of the CISC? Of the CISC, yeah.
It's just like you can do more stuff with like the instruction. You can execute more stuff with like one instruction. But if you reduce, you have to do more than one instruction.
Yeah, that's exactly it, right? Understood? So, I mean, and then in that regard, the CPU type of the from the Intel is register memory. The CPU type from the ARM and RISC V is the same. It's either register or load store. The load store and register is the same. And I don't want to even go and say what do I mean by register memory, right? Let me not waste my time. But it's in relation to what you said. So if we say that if I give you if I give you know that the CPU takes your C code, and then once you convert your C code to assembly language, the assembly language is actually the ISA of the CPU, right? So now if you write your C code like this, and then you write something like this, say, and eight by eight is equal to 4 5. So I've created an array, right, with two members of whatever, and then I give each of them, I give one of them 5, one of them 4. And then I say, and B is equals to 6 and C, right? And then I say C is equals to A 1 plus B, right? Have you seen this simple code, right? So now each CPU would, even though each CPU understands this code because this code will be converted to the ISA of that CPU, and then it will be able to execute it. All the CPUs will understand it. Either it's from Intel, ARM, or from RISC V, right? But the way it will execute this code or the way it will convert this code into the assembly language is what differs between the CPUs, right? So now if you write a very simple code like this in your mind, like this is a very simple code, like how you think about it is it's just doing some memory, some value is in memory A1, and then it adds that to B, and then it just gives the results to C, right? So you see that it's very simple, right? So what your code is doing is that this line of code, right, in the actual hardware, it will create space. to create a memory space. You saw that within your CPU, you have some two memories, and then you have the ALU and then the register file, right? So anytime you declare memory in your C code or in your high level language, right, it will go and create space within the memory, not the register file, but within the data memory. It will create space for storing A, right? So A1 and then A2. The values of A1 and A2. So the value of A1 and A2, one is 4, one is 5. So it will store 1, 4 here and store 5 here. It creates that, right? Now, when you declare variables within your C code, right, what does it do? Where does it store the value of that variable? Yeah, in the register file. So we have memory, and then we have what? Register file. So when you declare memory, an array, it will store it in the memory, the data memory. When you declare variables, it will store it in the register file. And then you must know that the register file, so you have the register file here, right? So it will come and store the value 6 in one of them and create space for C. Of course, there's no value at this time, but it will create a space for it. And then once you run your code, it will now, based on the architecture you are using, right? So if you study here, you must carefully note that you see this register file here. The output of the register file is directly connected to the ALU. The ALU is what does the calculation, right? You see that the output of the register file is directly connected to the ALU, right? But the output of the memory is not directly connected to the ALU. Are you studying it? Have you seen it? The output of the memory is connected back to the register file, right? So this is one CPU architecture, right? So it means that with this kind of CPU, right, for me to add a number that is in memory and to add a number that is in register file, right, it means that if I have numbers that are all in register file, it will be so fast because they are in the register file already. So they will be read to the inputs of the ALU, and then you actually do the calculation, and then store it back to the whether memory or another register file. But the issue will come in when I have a value in memory. I have some data in memory. I want to add that data to another number, probably in a register file, right? Because the memory is not directly connected here. So you have to use two instructions because in one cycle, right, the ALU can do only one operation at a time. It can do either addition, division. It can store a number in register file or memory. It can read a number from register file or memory. Understood? So if I have a number or a value residing within this ALU and I have this within this memory and I have this architecture, so it means that if I have something like A, C is equal to this is memory and then this is register file, this will not be done in one line of code. We will have to load where? Load this value from memory, from this memory to this register file. Then come and add. So that's how the hardware does it. Based on how it was designed, right? So when you take the CISC, right, the CISC are mostly register memory. So it means that the CISC has instructions in which, with only one line of code, you can operate on numbers that are both in memory and in register file at the same time, right? So if other than having something like load where and add, the CISC architecture has load where, so it can load from memory to register file, and then it has also add, and then it also has another one, add memory, something like add mem. So add mem to mean that I'm adding a value in memory and then a value in a register file, right? Now, but for the RISC, because the instructions are very few instructions, they want to use few instructions to implement a lot of things, right? So they only have load word and add word. So for me to add something that is in memory, I must use load word first, load the value, and then add then I get my results. So the advantage of using the six architecture is that you can use very few lines of code to execute or to get things done. But with the risk, the disadvantage is that you must write a lot of code. Now, because the disadvantage of the six is that because the instructions are so many, your hardware is very complex. Your hardware must have a lot of components. So, like here, right, we have memory. You see that the memory is routed to the register file. But because the six, we can read from memory and then from the register file at the same time and then operate on them. It means that I need a way to connect this memory to this register file. It means that this register file cannot only have only two outputs and stuff like that. This register file must be more complex than this. So it means that the architecture of the six is more complex. The internal architecture, it uses more gates, more wiring and everything. But because we are using very simple instructions, the internal architecture is very, very simple. And then it uses fewer gates. So that's that's the difference between the six and then the RISC architectures. Are we there? You see how easy that is? Okay, so and then I believe you have seen something like Indian names before. So the Intel architecture uses what is known as Little Indian, and then the ARM uses what is known as what Little Indian as default, and then the RISC also uses Little Indian. I hope you guys know what that is. Okay, so now the most important thing is that now the RISC V, as I said, is actually open source, and then the RISC V the RISC V architecture being open source have brought a lot of competition and then a lot of pressure on ARM, right? And then why has it brought a lot of pressure? Because once it's open source, right, now I can design a CPU, and then once I design a CPU with my RISC V ISA, I have to make it open source. Now, once I make it open source, anybody can actually see it, and a lot of people can actually improve upon it just for free. So now there are CPUs that are being designed for free, right? But that are also actually very, very as powerful as those ones designed by Intel and then ARM. So now there's a lot of pressure on Intel and ARM to also make their system open source, right? Now the important thing about this ISA being open source is that if you are designing a product, right, in hardware, as I said, we use the Verilog or VHDL to design your product. So what you do is that you write your code in Verilog. You use some commercial tools. We have one called Vivado. You use that tool to convert that code you've written into what is known as the GDSS file, GDSII file. Now this GDSI file is what we send to the foundry, and then they manufacture they manufacture the chip for you. Right, that's how that's the process you go through to manufacture an actual chip. You code in they call it hardware description language, Verilog VHDL. You use a commercial to extract the gate from your code. Then you send this gate. There's a file that you send to the foundry. The foundry will now manufacture a chip and ship it to you. So that's how it's done. So now imagine that you are designing, and then you need a CPU. Let's say you are designing some artificial intelligence kind of chip, right? That has something like you have a bus here, right? And then you have a model, a camera model. It will take some live feed from the camera, right? And then you have your DPU, deep learning unit or something like that. Then it takes the camera, an image from the camera, it sends it through the deep learning units, and then the deep learning image will display some kind of results. So you have to display here. We display some kind of results that it is your face or another person's face, whatever. But with a system like this, you need something to control all these processes, and that is where your CPU comes in, right? So now, if you're designing and then you need a CPU, right? Once you contact, and then you are designing to actually sell, right? Once you contact Intel for a CPU, you know that Intel is going to charge you for using the CPU, right? And then their CPUs are very expensive. So it means that even though you are sitting in your lab designing, so you are the designer. So you design this one is easy. It is easy to design. This is easy to design. This is easy to design, but this is very difficult. So you go and buy from Intel. So in effect, the price of your design has gone up because you are going to add the price of that CPU to the price of your design before you sell. Right? So once you're using CPUs from Intel or ARM in your design, the cost of your chip that you're designing is going to be expensive. You know that, right? Now, because open source CPUs have come, you don't have to go to Intel anymore. You just have to go online, go and pick that open source CPU and use it within your system. And then it's free. So once it's free, it means that there's no cost of the CPU involved at all. So your product becomes cheaper and cheaper and cheaper. Right? Of course, there's a downside to both, right? Now, if you're using Intel CPUs or ARM, you know that it's actually proven. They have tested it over and over and over and made sure that there are no bugs or errors. But if you go and pick a CPU from online, you must know that you're going to run into trouble you're going to run into trouble someday because probably they've not tested some kind of inputs. So that is the disadvantage. So if you don't mind that probably one day something will happen, then you can go for the open source one. And then with the Intel ones, once you develop a product and then you have a problem, and then the problem is with the CPU, you know that they will have to give you back your money. But with open source, once something happens, you know that nobody cares because you actually pick it up for free, right? And then the last important thing about using the open source IC and then the closed source IC is that nowadays there are some kind of chip some kind of chip wars within Europe and then Asia, within China. You know that every product is made in China, right? So there's some kind of a demand that each country produces their own kind of chips and then their own kind of components within their chips. Why? Because now people are actually fixing Trojan horses within codes, like within the chips, right? So if you buy an Intel CPU, as I said, they give you a black box. You don't have access to the internal architecture of it. You don't know what it's doing. You don't know what each line of code is doing. So they can easily hide a Trojan horse inside there. So you develop your product and then it begins to leak information somewhere, right? So now, once you use an open source, because the code is available to you, based on your experience, you can go through each line of code to make sure that there's no malicious hardware within it, right? So this is just exam questions that I'm just giving you out for free, and then it might not be here, but as I said, once I say it, I'll go and set questions on it, and if you say I didn't say it, I'll show you the video there. Yeah. Any questions so far? So now let's go into the RISC V. So as I said, once you understand what this sheet is for, then everything becomes easier. So we are going to go over this one so fast, right? So the RISC V ISA, this is the RISC V ISA. So this is all you need to design the RISC V ISA from the scratch, right? You need this to design the RISC V ISA, right? Understood? So the RISC V ISA, we have three base integer ISAs. We have the RISC V 64i. So if I say RISC V 64, RV 64i, you know what that means? RV means what? RISC V. 64 means what? Yeah? And then what does the 64 bit mean? What does the 64 bit mean? Or the register. So the RISC V has RV64i. The I just means integer, right? So if I say this CPU is RISC V 64i, it means that this CPU can only do 64, the register file data weight is 64, and then it can only do integer operations. I means integer, so only integer operations. So what if I want to do decimal operations? It means that I can use the RISC V 64I. I have to add something to it. But the RISC V, the RV32I is the base IAC. They call it the base IAC. So anytime you are designing any type of RISC V CPU, this RISC V 32I must be part of it, right? So it's the 32-bit version of the integer IAC. So if I want to add probably division, right, I must come and do RISC V 32I then something. So I've added division operation to the integer operation and stuff like that. So easy stuff like that. So here, so there is 5, 32, 64I and stuff like that. So the integer operations are all here. Have you seen them on your what? Here. So I can see that we have categories. We have loads. You can see something like load bytes. Have you seen this? You can see load half word, and then we have the assembly language is there. So if I say load byte, you must know the structure of that or the structure of that assembly language, right? So load byte would be LB. Have you seen RD? RS1 and then what? Immediate. Right? So you must know this kind of architecture or this kind of structure. And then you must know it all in your head because in the exam I won't provide you with this sheet. I mean, it's just the basic. It's just basic. So this is known as the green card, and then you know what a green card means, right? The green card of RISC V. So once you have this, you can enter into any RISC V. Right now, your second sheet gives you what we are going to do right now is the instructions. That's your second sheet, right? So your first sheet will give you the assembly kind of code, RD, this. Your next sheet will give you the machine code, right? So you take your assembly language and then you convert it to machine code, and then you have a 32-bit kind of weight, right? And then each field means something. So that's what we are going to study. As easy as that. Okay, so but first of all, you must know that we have studied register files, right? The RISC V also has register files. As I said, each CPU has a register file. The most important thing is that the RISC V has 32 registers, right? So the RISC V, the total number of registers here is 32. So from register 0 up to register 31. And then we label it X. So X0 to X31 is fixed. Right? And then the data weight now, that one will depend on whether we are doing RV64, RV32, or RV128. But here we are mostly doing RV32. RV32. So here it will be 32 bits. So the data weight of your RISC V is 32, and then the number of registers within the RISC V is up to only 32, right? Another very important thing is that the X0 here, you cannot write any value to this X0. The X0 is fixed to 0. It's stuck at 0. It's hardwired to 0. So you can write to any location here, but you cannot write to this location because it's fixed to 0. Another very important objective question, right? The RISC. Okay. I mean, very easy. The RISC V X0 register is fixed to what value? So 0, 1, 2, 3, some stuff like that. Yeah, stuff like that. Right. So now we have the RISC V data types, and then these are stuff. These are stuff you know already. The data type is 1, 2, 3, 4, or 8 bytes and stuff like that. Right. So now the most important thing is that now if we take each each assembly here, right? How do you encode it? So it's very very important. How do you encode it? So how do you take this uh, something here, an assembly code here, and then how do you encode it using something like this, right? So the first thing is that we are doing the RISC V has a length. The instructions of the RISC V has length of 16, 32, 48 going like a lot of them, but we are mostly going to be fixed on 32-bit instructions. So it means that our instruction length, it means that we have, don't always confuse the register length and then the instruction length. The instructions are stored in our data memory, right? Right? And then we have instruction length of 16 up to whatever, but we are going to focus on 32-bit instruction length. Understood? Understood? So now, if you take if you take the 32-bit instruction length, now have you seen the 32-bit instruction length? The most important thing is that if you study here, the most important thing is that the first 2 bits is stuck at 1 1. Have you seen it? So another objective questions. So these are just objectives, right? There is 532 bits. The first 2 bits are stuck at what? 0 0 1 0 1 1 and stuff like that. So you can see that it's stuck at 1 1. Right? So when you write the 32-bit instructions, the first 2 bits are always 1 1. Then the rest change. Understood? Now this is how the length of so once we are dealing with only 32 bits, right? This is the length of your instruction. It's 32. It's 4 bytes. You know, 4 bytes is one word. If I say one word, it's what? 4 bytes, right? 4 bytes is what? 32 bits. So it starts from 0 to what? 31, right? And then you must know that we divide the fields here, and then each field has a meaning. We are going to divide it using a sheet like this, right? So now, based on the operation you are doing, right, you can have the format of the instruction can be R type, it can be I type, S type, U type, SB, and then UJ type. But we are going to focus mostly on the I, R, S, and then U type, right? So I've made it easy for you. Once I go into this stuff, then you guys become confused, right? So now, all the instructions are encoded based on which type. If I'm doing addition, you know that if I'm doing addition and then I'm doing addition of 2 register numbers, right? It's going to be different from if I'm loading number from memory. So it means that the instructions to do something like addition, subtraction is different from the format to do something like loading or storing some value in the register. So that's why we have formats. Understood? So as I said, we have the R format. So the R format means that I'm operating on values, or I'm using instruction that has 3 register inputs. Understood? So if you take an addition, add, right? So I add, so if I have add x1, something like x1 is equal to x2 plus x3. So it means that I'm using 3 registers, right? I add 1 register value to another register value and store it in a register value, right? So add, XOR, multiplication, and then logical operations all use 3 registers. So all of them are grouped into one format, known as the what? The R format, right? We also have a format known as the I format. And then the I formats are instruction with immediates. You know what immediates are? So now, you see that if I'm adding a register value and another value that is a register, and then if I'm adding something like x2 plus 10 is equals to x1. Now you know that this 10 is a constant. It's not in register. It's a constant. So I need to know how to handle it. Right? So that's what the I type is. So the immediate in hardware just means constant, a constant number. And then we have the S format. Now, if you want to store, right, store values within. So the store just means that I'm actually storing a value in a register file, or I'm storing a value in memory. It's as easy as that. Any questions so far? I hope you are understanding. Eh? Oh, don't worry about it. And that is advanced. I don't want to be good. Eh? Yeah, yeah, yeah. Yeah, not even the you won't even touch the. Okay, so now this is so as I said, this is the format. So this is 32 bits. As I said, the instruction length is 32 bits, and then we have the format. So each one has its own format. So we have the R type. The first 7 bits is known as the opcode for all of them. That one is fixed. We have an opcode, we have an RD, func2, RS1. So you will know what each of them means. So we have the R type, I, S, and U, and then each of them formats are grouped differently. But what is important is that the opcode is fixed to the first 7 bits, right? And I said that for the 32-bit instruction length, the first 2 bits are stuck at what? Yeah. And then you must know that once you are doing immediate, so immediate, I say that immediate means a constant, right? So immediate means that I'm adding a register value and then a constant. So that constant value, you see that this register file, if I'm doing R type and I'm adding, let's say, one register to another, and then storing it in another register, what I will need is I will need RS1, which is the source register, RS2, another source register. So those 2 registers, RS1 plus RS2. I need a register to store it in. And then that register will be RD, destination register. Understood? So I take RS1, the value, understand that this RS1, once I put a value here, it's not the value I'm adding actually. It's the register location, right? So it means that there's a number within this register. So if I put, let's say, 5 here, it means that go to register 5, pick out a number there. And then if I put, let's say, 4 here, go to register 4, there's a number there, pick out that number, add those 2 numbers, and then if I put, let's say, 6 here, add those 2 numbers and store it in register 6. Understood? The way that your eyes are red for now, but this I guess easy stuff. Once you go and sit down and you just take some 5 minutes and then you understand it. Now, as I said, for the I type, we are dealing with constants, and then the constant is not stored in a register or memory. The constant is stored within the instruction itself. So we have to create space to store the constant. So you see that for the I type, we have the opcode. So if I'm adding, let's say, the value in register 10 will be added to a constant value, and then it will be stored in the RD. You see how easy that is. But you must know that you see that this one is what? 11:0. So it means that it's a 12-bit number. Understood? So if I say, what is the highest number a 12-bit number can store? I hope you know the answer to that. Another very basic objective question. Right, so this is how the I format looks like. And then so there will be questions like, okay, in the I 32-bit length, right? What is the number of bits used for the opcode? So here is 7. What is the number of bits for the RD, the destination register? It's what? 5 bits. What is the func3? 3 bits. RS1, RS2 are 5 bits, and then func7 is what? 7 bits. Now you must know that why do I have opcode func3 and then func7? Now sometimes the opcode alone cannot be used to identify the operation, right? So you need help from the func3 field and then the func7 field. So sometimes the opcodes are the same, like the opcode for add and subtract is the same. So I have to come to func3 and then func3 field here and then function 7 field there to be able to identify if I'm doing addition or not. And I mean, you can go, you can check on your sheet here. So look for add. Have you seen add? Now look at the opcode for add. Have you seen the opcode for add? Have you seen the opcode for subtract? You see that they are the same. So how do I know that this operation is addition or subtraction? I need the funct3 field and then the funct7 field. Understood? Yeah. So now once you go and then the funct3 is the same, then you go to the funct7. Have you seen it? All right. So okay, another very important question: why do I use 5 bits to represent the so for the R type, why do I use 5 bits to represent the source register, destination register, and then source register 1, register 2, and then the RD? Why do I use 5 bits? Hurry up, hurry up. They're just a basic question. Huh? What is 32-bit register?
Two and
Yeah, so it means that I have 32 registers. So how many bits do I need to address the 32? 5. So they don't choose those numbers just like that, right? Each number has a meaning. And so we use 5 bits for the RS to RS1 because we are referring to the register files. Right? And then there are only 32 register files, and then I need 5 bits to be able to address 32 locations within the register file. Right? Okay, so now it means that if I have something like this, so you know that the addition, right? If I do something like if I'm doing addition, something like add x5, x6, x7. Now these last two registers are the source and destination registers, right? The source register 1, source register 2. The 5 is the what? The register. So I do, in effect, in case you see something like this, we are doing x6, register x6, the value in register x6 plus the value in what? Register x5. And then we are storing the results in what? X5. So now I can tell you that I can write something like this and say, give me the field, right? What will be stored here? So you must know that we are doing addition. And then the opcode for addition is what? So you have to go through your sheet here again. So you just check addition. Aha. So now what is 0, 1, 1, 0, 1, 1? This 0x means what? Hexadecimal. So I have to know how to convert my number to hexadecimal. As easy as that. No. So now here you know that what is this code? The destination. So it is store 5 here. What is this field? Funct3. So you have to check your sheet to see what is funct3. So that's why there's 0 here. Then what is this register? RS1. RS1 is what? 6. So what is here? So you see how easy that is. And then what is here? So you see how easy that is. So once you know what you're doing, but if you don't know what you're doing, it means that that's 0. And then if you get even 1 bit wrong here, everything is 0. Understood? So as I said again, sometimes the opcodes are the same. So the opcodes for the R type are all the same. So the I type are add, sub, shift left, logical, and stuff like that. All the opcodes are the same. Have you seen it? So I have to use the funct3 and the funct7 to be able to identify it. As easy as that, right? Shall I continue? Now that we know how to add numbers in registers, right? So what if right? So what if I have something like yep.
opcode all being the same,
Yeah.
does it mean that they all follow like a similar execution pattern?
Yeah, they all follow the same execution
Add,
pattern.
subtract, multiply,
Yeah, yeah. And then if you think about it, like add and subtract, you are dealing with three registers. You are adding one register to another, and then you are storing it in another register. Subtract and stuff like that. XOR. If I say XOR, right, you take one register, you XOR it with another register, and store the results in. So they all follow the same kind of format. So that's why they are all grouped together. Pardon? Shall I continue? So I know how to store. I know how to add, subtract. Right? So now let's go another further. Let's see how to add constants. If I have, I mean, these are just easy stuff like it. So if I have something like in case I write my C like it's A B C and then I say A is equals to B plus 10, right? So you need to be able to convert this one into the RISC V assembly code, right? And then to be able to convert that RISC V assembly code to the machine code, which is this one, as easy as that. You see how you see how interesting it is. Okay, so now basically the same thing. So in your exam, the simple thing you ask is again. I have my I32-bit length instruction, right? What is how many bits is used to represent the opcode? The RD from 3 RS1. But you know, so here something has changed here. Instead of so if I'm adding a constant, right, it means that I don't need RS what? RS2. So they've replaced the RS2 with the constant number. You see that this immediate, I said immediate in hard wages means constant, right? So you have your opcode RD, RS1, then your immediate, the constant number. And then the constant number can be 12, can be a 12-bit number. So it means that what is the highest number I can store? What's the highest number I can store? Let's say I say that okay, the number is a 12-bit unsigned number. What's the highest number you can store? Uh, you guys don't know that simple calculation. Eh? Like something like if I have something like if I have something like a 4-bit number, and then I say this number is signed, right? What does it mean? It means it has both negative numbers and what positive. So I need a way to identify negative numbers and positive numbers. How do I identify if a number is negative or positive in a 4-bit number? How do I identify it? If I have something like 1010, is this number positive or negative? Ha! I said you have a 4-bit number here. It is unsigned. Oh, okay, it's signed. Is this number positive or negative? Positive or negative? So you see that this is where if I set objective question like this, I don't want you to guess, so I'll give -1 if you get it wrong. So that you don't have to be guessing just like that. I mean, you must know. So is this negative or positive? Negative. Why? One. So it means that for signed numbers, I use the MSB. We call it MSB, right? Most significant bit to identify the number. So if I have 1 here, it means that this number is negative. If I have 0 here, this number is positive. So it means that if I want the highest number that this 4-bit can store, right? Because this one is used to identify the number, it's not part. So the highest number this one can store is 111. So 7. That's the highest number it can store. So the formula will be what? 2 to the power 4 minus 1 minus 1. Signed number. Right? So it means that I can store negative something too, but the highest I can store is 7. So if I say this number is unsigned, right, it means that I have only positive numbers. And then unsigned means that this whole number is used to identify the number. So instead of this one being negative 7 in sign, instead of it being negative 7 in sign, it becomes what? 1 0 1 0 is what? 1 0 1 0 is what? Hey.
Oh,
Okay, but the most important thing is that, so if the number is unsigned, I have to use the whole 4-bit to identify the number. So it means that the highest number for an unsigned is 1 1 1 1, which is 50. Right? So if I say the RISC V, this immediate is 12-bit unsigned. Right? It's a 12-bit number, and then it's a 12-bit number, and then it's unsigned. What's the highest number I can store? It's signed. Let me put it that way. It's signed. What's the highest number I can store with 12 bits? I just explained this thing right now. Hurry up, hurry up, hurry up. So it is 2 to the power 12 because it's signed. One bit is used to identify the number. So I have to move that one, right? Then minus 1. So this is the highest number. Yeah, probably. Okay, so now the next thing is what? Okay, the next thing is this. So I know how to add or XOR numbers or whatever in registers. So 3 registers, right? So the R type. I know how to add a number to a constant and store it in a register using the I type, right? The next is memory. So how do I load or store values in memory? I need another format for that also, right? So now you know that you know that memory you build. I think I explained when we were talking about memories, right? I showed you how to combine smaller memories to form bigger memories, right? Right? Right. So I said that in computing, like mostly they were the first memories that were made, right, were mostly 8 bits in weight. So pay attention here. The first memories that were made, the first memories that were made were 8 bits in weight, right? 8 bits in weight. Each memory was just fixed to 8 bits. They didn't design 16 bit and 32 bit and stuff like that, right? So it means that for me to address this, the first location, it will be what? 0, 1, 2, 3, 4, going, right? Now, if I want to combine, if I want to design a system that has 32-bit data weight, I'm not talking about the length, the data weight. What do I do? So it means that I need to buy 8 bits, then another 8 bits, another 8 bits, another 8 bits. But the way I store is that I don't just put this 8 bit here and go and put the other 8 bit on top. Now it means that it will be some kind of continuous. So I have to put up another 8 bit here, another 8 bit here, another 8 bit here. So this is 8 bits, 8 bits, 8 bits, and all of them can store 8 bits, right? So when I'm addressing, so here, pay attention. So when I'm addressing, and then I say that I have data in. So in case I'm storing the data, right? I'll have to store. I don't store the data if I have data like. You know that this is 8 bits. You know that if I have something like 8 8 4 4 5 5 6 6. This is hexadecimal. In hexadecimal, each number is what? 4 bits. Right? So if I tell you that store this number 884455 and 66, right? Now you cannot store this number 88 here. You come and store 44 here and stuff like that, right? Because this number is just a 32-bit number, and then all must be stored in one location, right? So what you normally do, copy, is that you store 66 here, 55 here, but 44 here, and 88 here. But you must know that when you are addressing it, this location is 0. This location is what? 1. This location is 2. This location is 3. Right? So now, if I go up, so now, instead of here being 1, all of this have changed, right? So this has become what? 4. Then 5, 6, 7. Then you go 8. Then what? 12. So now, you always reference the first memory. So we say that in computing, we normally say that the addressing is byte addressing. So why do we say it's byte addressing? We address the first location. So if I address location 0, I don't address location 1 or 2 or 3. I just say go to location 0. What I mean is that go to location 0, 1, 2, 3. Read the whole line. So if I say go to location 4, I mean 4, 5, 6, 7. So we do, that's why we say we do byte addressing. Yeah. Understood? Simple, right? So now, the most important thing is that how do I store? Very important. Each computer stores this number differently. Like how I've arranged it, right? Each CPU will store it differently based on what is known as the Indianness. So, do you store from the right? So does the right value go to the lowest address, and then the others will do, or I store from the left, right? So there's always confusion there. Then they call it the Indianness war. Yeah, so and then the CPU designers could not come to an agreement, right? I mean, everybody said that, some said that, storing it from the left is good. So if in case I'm storing a number here, somebody will say, oh, storing this number here, this number here, this number here, and then the last one here is better than storing this one here, this one. So they didn't come to an agreement. So each CPU designer does what they want, right? So that's why once you take a CPU, you must know whether it is Little Indian or yeah. Yeah, so each CPU will tell you, oh, me, I use Little Indian. So when you are handling their data, you have to be careful and see how the data is arranged. So we have Little Indian and then we have Big Indian. So for the Little Indian, so as I said, in computing, the lowest number is known as the LSB. You know that already, right? Least significant bit, and then the highest number is known as what? MSB. Most significant bit. So the Little Indian, this means that the LSB of the data is placed in the byte with the lowest address. Understood? So for Little Indian, I take the LSB, this is the LSB, 66. And then I place the LSB in the lowest address. So 66 will be stored here, 55 will be stored here, 44 will be stored here, 88 will be stored here. Big Indian is the opposite, right? The MSB is stored in the lowest address. So you must be very careful. So if I say MSB, it means that if I say Big Indian, it means that the Big Indian will come and take the MSB. Instead of putting 6 here, it takes 88 and store it here. Then go 44, 55, 66. Easy as that. Right? So in case I give you something like, so in the exam I can give you something like this. This is Little Indian. Store the value within this memory. So you know that the LSB is stored in the lowest address. So 001122 then. Going. Then here, if I say this is Big Indian, store the same number in Big Indian, you know that this is 33 what? 221100. As easy as that. Are we okay?
So on storage, the zero, you need to show that it's exact.
Which one? The 0x, yeah. Once you say in computer, once you say 0x, it's hexadecimal.
And you see the way they are combined in between.
Yeah, yeah,
But they are register files that are for extension.
yeah. Hmm?
And they register
Yeah,
files.
nowadays. But they still use the byte addressing. So you see that with the, if you pay attention, I don't know whether you have coded, the PC is always incremented by 4 instead of 1. Have you seen that before? You always see PC plus 4 instead of PC plus 1. When you are implementing the PC, I said that the PC store the next address. So it is always plus 1. You see PC plus 4, if you see in computer everywhere, it's because they go from 0 to 4 to 8 to, that's why they do PC plus 4 instead of PC plus 1. Are we there? Okay, so this is the format for the I, right? If I have so it means that to store a number, right? Or okay, we are loading numbers, right? The loading numbers also use the same format as the I format, right? You have the opcode, RJ function, and then you have the immediate here. Now, now, if I say load a number, what what do I mean? If I say load, I'm loading a number. So if I say load, right, I have memory, and then I have register file, all have addresses, right? 0, 1, then whatever. Let's do 0, 1, going, right? So if I say load, right, all I mean is that there's a number in memory. I want to bring that number and store that number in what? Register file. It's as easy as that. So it means that um, common sense, right? Again, if I want to, if I want to execute the load instructions, right? What do I need? Just what do I need to be able to load something, go into memory and bring that thing out and store that thing in register file? Address of what? The instruction. The instruction is what we are doing. So as I said, we have memory and register file. So what address am I looking for?
Where you are loading it.
Hmm?
Where you are loading it.
Yeah, so you need the address of the register, the destination. So I'm loading something from memory. So the first, one thing I need is the address of the register. Where in the register am I loading it? So you can see here that we have destination here. So that is where we store this one. So if in case I put a number here, so it means that I'm loading something from memory and then I'm storing it in that destination. Now I need another thing. What do I need again? No, you don't really need it. No, no, no. No, 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 no. This one is different. This one is different. So now you need the address of where in memory that value is stored. Common sense, as I said. Right? Common sense, right? So now, but I mean, common sense is not that common, right? So, yeah. But I mean, you have to know the location within memory that that value is. But the way they've done it is that first of all, once you create your instructions, right, you have to give it what is known as the base address. So the base address is where your address is starting. So you know that address is in memory, it can start from anywhere. So you give it a base address. So in case I want to know where my value is located, I have to go into my instructions, and then the instructions always has a base address. So they always give me a base address, probably, and then mostly it starts from 0. So it means that this memory starts from 0, right? Now they give you the base address, and then they give you what is known as the offset. Everything here. So they give you the base address. The base address is the the base address of your memory, normally 0, right? And then they give what is known as the offset. So what you do is that you take the offset plus the base address, is where that value is located. So you have a 12-bit offset over here. So you take the offset plus the base address, then it will give you the location of where in memory your value is, and then you take your value and then you store it in the destination register. Simple. That's how you load. Right? So you'll be given something like this. Load word x14, 8, and x2. Right? So you must know what each field represents. Right? So you have your opcode, which is load, and then your opcode for load is, if you check your sheet, the opcode for load is what? So you have your opcode for load. Your next is your destination register. So once you see LW X14, the first value here is your destination register. So you put your destination register here, so it's 14, right? And then your next is the base register. So the base register, so if you see 8 X2, it means that X2 stores my base register. So the base register is 2 here. And then the next is the offset 8. So you store your 8 here. Simple. Then you continue, right? Now you can store, you can load from memory, right? Now the next obvious thing is what? Store. And then store just means what? The opposite. I have a value in my register file. I want to pick that value and then put that value in memory. Common sense. What do I need?
Destination address.
So the store is just the exact same thing. You need your opcode. Then you can find your opcode of your store on your sheet. Then you will need your offset again. But here, understand, you see how it's arranged. The offset is broken down into two. The 12-bit offset, right? Part of it is stored here and part of it is stored here. So you combine the value here and then the value here, and then you get your offset. So you have to be careful. Right, and then you have your function, you have your RS1, and then you have your RS2. What is the RS1 and then your RS2?
First one is the destination. RS1 is the destination.
You also need the base address. Okay, so the last thing we do, then we go is, so now I'll just give you a simple kind of C code or Sindo code. Okay, let's say a Sindo code, and then I'll ask you that give me the RISC V version. That's easy. So you just, if I say in C, A is equals to B plus C, and then I say the value A is stored in register X1, B is X2, C is X3. So what is the RISC V version of this? So you know that it's add X1, X2, X3. Easier. So if I say D is equals to E minus F, what is the RISC V version of this? You know that it's sub X2, X4, X5. Easy as that.
The case doesn't matter.
Which case?
The casing of the capital letters.
Or not? I mean, they're all small letters. Yeah, but use small letters. Okay, so now if I have something like this, A is equals to B plus C plus D minus F. How do you think this will be done? So X10, probably X9, X8, X7, X6. So these are the register suites you must use. So if I give you something like this, and I say, give me the RISC V version, what will it be? X3, X10. So you add X9, X what? Uh-huh. Sub what?
No, they will still do it. You add X10, X9.
X added way.
You then another instruction.
So I come and do another add here.
Okay.
Uh,
X10 and X10. Yeah. Then sub
yeah,
X10.
that's you see, 10 marks, easy as that. It's as easy as that. So, and I thought, and I know that somebody will say add X1, X10, X9, right? Somebody will add the entire thing in one line, but the most important thing is that you do one operation at a time. You cannot do two operations. So that's how you break it down. So you see how easy that is, right? X10, X9. How do I do this? Huh? We are still using registers. F is equals to G. Hurry up, then we are done. Very, very simple. F is equals to G. There's no load involved at all here. There's no store involved. There's no memory involved there at all. They are all still registers. I have register X. Now I have something in register X. I have something in register X9, right? I want to put it in register. Yeah.
X10 and X9 and then X0.
You want the 20 marks. Why?
Since 0 is hard to get, 0% number.
As easy as that. So the register X0, I said register X0 is hard to predict with 0. So if you do X9 plus X0, it's still the same thing. And then you store it in X10. Easy marks. All right, we are done. Any question? Yep.
When we are doing it by 4,
Yeah.
Registers.
Yeah.
So I wanted to ask, since 0 is hard to get, the register
The byte 4.
4 by 4, does the X0 really hard to get right to the
That what?
the whole row.
No. Those ones are the addresses. They are not the values in the register. No. They are address 0. And then we refer to this memory location address. And then once I combine those memories, I'm not talking about register file. No. The register file is where the X0 is hard coded, not memory.
So the memory itself is what?
It's completely different from the register file. No, the register file is just 32 bits with it's fixed. Yeah, that one is fixed.